There have been a number of parameters that I have seen discussed very differently throughout the years in the hobby, and a lot of the time I hear people or see discussions online, and I don't know much, but I can blatantly tell that they're not correct, or at least all the information is not there. So a couple of these parameters, torque, efficiency, 4S, 6S, these stuff, they have many different possible explanations, and there's a lot of people trying to figure out why things are different and why things are the way they are. And I'm one of those people. However, I'm not an engineer, and I don't do the engineering behind it. Also, I would add that this stuff that I'm going to be talking about, I am definitely not qualified to discuss. I don't have an engineering background. I don't even have the physics knowledge to explain the vast majority of it. However, I have developed general intuition around the topic, and I have cross-referenced my intuition with various engineers. So take that with a grain of salt. What I'm about to tell you is not fact. And in reality, we don't even know the whole story. We don't even know all the information. So it's still developing. A lot of this also comes from Ryan Harold of Miniquad Test Bench. He has done just heaps of work on this. I really wish he would write more articles because every time I talk to him, it's so freaking interesting. Okay, let's start with torque. What is torque? I have evaded torque in my discussions for a long time now because people don't recognize it, I think, correctly. The vast majority of people that I hear talking about torque often think that low kV means higher torque, and they think, oh yeah, I want that low kV grunt. Or people that go to buy motors, they think, okay, what's the lowest kV? Or the flip side, the racers will think, what's the highest kV I can run? Which maybe neither one of those are really 100% accurate. There is no real 100% accurate, but let's talk about what torque actually is. So first and foremost, mini quads fly with torque. Without torque, these things don't function. The prop has to transition from one speed to another, and that is what the torque does. It gives you that ability to just pop the throttle. It's not like your actual throttle, not like the actual throttle stick. I mean, the flight control will just pop from one RPM to the next RPM with no transition time in between, and that is how these things work. However, the stump pulling torque that people typically think of like a car with a low gear is not accurate in any possible way. So what is actual torque? I'm going to try to explain the torque of these motors with an example in another area. So everybody's ridden a bike. When you ride a bike, let's think about a fixie bike, a bike with one gear. This bike only has one gear, so it has to be geared to a particular speed. Anybody that's ridden a fixie knows that it's not geared to go slow. It's geared to go maybe 20, 30 miles per hour. So it's a gear that when you try to get the bike moving, or if you try to start a fixie bike going uphill, you can't. It's too high of a gear to put pressure on to start. And so let's think about how you actually ride a fixie bike. When you start riding a fixie bike, you usually stand up on the pedals. You put all your weight into it. If you were to just use your leg muscles to try and get the bike going and actually rolling, it would take a lot of leg force, a lot of leg energy to actually get that bike moving. Once you get up to the optimal speed range of that one gear that the fixie bike has, if you didn't know, fixie bikes only have one gear, then you can actually modulate the speed pretty nicely. There's this range of speed in the middle that you can go faster, slower, you can do everything. Your legs are able to manage the speed with not much difficulty. You have the muscle power, you have the RPM power of your legs, your joints do spin properly. Once you get going too fast, or if you try to ride a fixie bike downhill, if you take your feet off those pedals, it's a fixie bike. Those pedals are spinning if that rear wheel is spinning. If you take your feet off those pedals, you're not getting your feet back on, and often fixie bikes don't have brakes. This is similar to our brushless motors, or at least this is the best explanation I have for how our brushless motors work. A motor of a particular size has a particular RPM range where it is optimal at. I'm not saying it's the max power or the max RPM. Obviously, going up higher in RPM is going to give you more thrust power. But I mean, where does the motor actually produce the best torque, or the most effective or most efficient, or where is the range at which that motor can produce torque? Another example is something like putting a car on a dyno. When you put a car, specifically like a Civic or something, on a dyno, you'll start spinning it up, and then the dyno reader, whatever gauge, will start going up, and it kind of goes up slowly, slowly, slowly. And then once it gets to this optimal range, usually on like 8,000 RPM on a Civic, it kind of pops. The power pops real fast, and then it starts to taper off again. This is what I mean by the torque range of the motor, the optimal torque range of the motor. And going back to motor sizes, the wider the motor is, the lower you're moving that torque range. And the reason why I don't like 23 size motors is because that torque range is so low that it's really hard to manage the throttle when you're trying to fly low, when you're trying to do really delicate acro moves around small objects and fine things. Now, the 23 motors, 2306, does not technically have more torque than a 2207. And Ryan has also confirmed for me that the 2207 on the bench in his tests have more torque than a 2306. Now, I attribute that to the greater stator volume compared to I'm talking about motors of the same exact construction, compared to a 2306. So the 2207 will have about 6 and some change % more stator volume than a 2306. However, that torque is played out in a different zone, a different area of the RPM range. The 22 size motor, the smaller motor, will have that torque higher up in the RPM range, and the lower RPM range will be very, very soft and mushy. The 2306 will have that torque range lower-ish. I think a whole lot lower. It's really hard to gauge where it is, but it feels to me like it's a whole lot lower. And that torque pop that happens really, really low in the RPM, where the props are making thrust or going through their thrust phase transition, where they're not making thrust to when they are making thrust. And so it becomes really difficult to modulate the throttle for flying low and doing all that stuff. However, in big air moves, like big free air falls and things, the 23 size motor does definitely feel better. So to me, this may be wrong, and Ryan tells me it's wrong, but the 23 size motor does feel like it has a better hold on the prop. I don't even know how else to explain that. So in the air, when you stop from spinning or rolling or anything, the 23 size motors tend to feel more solid in their stop. Now, this is a really, really fine difference, and it's something that you can really probably only tell after flying for quite a while or being very skilled or trying a lot of different products. But there is definitely a difference in the 23 size motors. They do feel good in some ways. However, it's that throttle range that doesn't feel good. Now, a lot of people will jump in and say, well, you can just put a throttle curve on there and it's going to make everything better and it's going to fix everything. I don't like throttle curves. I'm always changing my throttle endpoints so that throttle curves change that completely. Also, the throttle curves make the motor unpredictable, and it's just weird. I don't like software. I prefer everything in hardware rather than software. I want everything as much as I could possibly have in hardware. Now, this may just be a pet peeve of mine and something that I prefer, but discussing software parameters for a particular product just to make it work properly, that doesn't make total sense. I might as well just use the product that works properly out of the box and not have to do any software magic. Now, the 2207, 2208, and the reason I went to 2208 is because it improves that control feeling compared to the 2207. It just improves that control feeling, and that's why I went to 2208. That's what I wanted, and it did give me that. However, it's still not like a 2306. A 2306 does still feel just slightly more, best word I can say is solid on various movements. However, the throttle range at the bottom is really a pain, so not good. I definitely prefer the 2208. Now let's talk about KV. KV is something else that's totally different. People often say, I want low KV because I want torque. And now we know that the KV has nothing to do with the torque of the motor. Yeah, okay, it can change some minor things here and there. But let's think about where the torque band is. Let's say we have a 2000 kV motor and the maximal torque range is right at 50%. So 2000 kV motor at 50%. Let's now take this motor and push it up to 3000 kV. Well, the optimal RPM range for where the torque lies isn't changing. It's still going to be optimal at a particular RPM. And you've just pushed the kV even higher. So now what has happened is that the optimal throttle position for the torque has dropped tremendously. So now I hope that makes sense. So if you're 50% and you're at 2,000 kV, and then you go to 3,000 kV, that 50% maximal torque range will drop to, like, let's say 35% or 40%. So you have effectively lowered where the torque falls in the kV range, in the whole RPM range, not the kV range, in the throttle range from 0 to 100. You have lowered where the maximal torque lies. That may be a good thing for some people, but it's also the opposite effect that people think. People think lower kV is going to give me more torque. No, that's absolutely false. In fact, higher kV is going to give you more torque at the bottom of the throttle range. This is exactly what I feel in motors. The problem with higher kV is that you get to a point where the motor no longer can produce torque to keep spinning the motor faster and faster and faster. It literally does not have the ability to keep spinning the motor faster and faster. So now you have this huge top range, if you have super high kV, top range of your throttle that does effectively nothing. And this is what I'm now feeling, and is much more evident in micros. Like I've said in the past, micros exhibit all things accelerated and just expanded. They just exhibit all effects much more than a 5-inch quad. Everything is amplified on a micro. So with these little tiny 0802 motors on 12,000 kV, I feel like the top 25% of the throttle range is useless, pretty much does nothing. And if you look at my previous videos, you'll see that when I'm flying, I don't even use the top 25% of my throttle range. I might as well just cut it off. So that tells me that the kV of the motor is too high. You need to lower the kV in order to haul it back into the proper range and give you more throttle resolution so that it's easier to modulate the throttle, because it's really hard to fly when you only have 2 millimeters of stick travel to fly. Anyways, let's get back to a 5-inch and bigger discussion in general. What I don't know, and what I still cannot figure out, or nobody can really explain, is how does the wider motor change the quality of the torque when you go through the RPM range? I'm not even going to expand on that anymore because it's so out there that I can't even think about it myself. This is what I think about normally when I'm trying to just think about these things and just think. Anyways, that is torque. That's my best explanation of torque. There's a ton more information about it out there, and I don't know if I did the best job of explaining it, but I hope that I explained it in a way that's very understandable to everybody. Now, the next topic, efficiencies, 4S, 6S, all these things. Now, that's even more curious and more out there, and we are trying to figure out what on earth is so different about 6S that makes it feel so different from 4S. And we still don't know, but we're kind of starting to guess. So let's look at some other examples. Let's look at the Phantom. The Phantoms, the older Phantoms were running on 4S, and they were using 2212 motors, I believe. The motor is kind of insignificant, but they're running on 4S. And then when they moved to the Phantom 4, I believe, they moved to 5S. Now, why did they move to 5S? And then let's look at I'm using DJI as an example because they are arguably the biggest drone company in the world, and they've done more research on this than anybody else could possibly have done. So whatever they have out there in the market is probably highly, highly researched and highly optimized for their purpose. So now let's look at the Mavic. Now the Mavic is like, I think the name of the Mavic came from because that it sounds like magic, because it literally is like magic to me. How can this little tiny thing with 1806 motors and 7-inch props, 1806 motors and 7-inch props, fly for 30 minutes in excess of, I've flown a Mavic for like 35 minutes before. How on earth is this thing flying for that long? Yeah, of course it weighs less than a Phantom and everything, but geez, it only has a 3S, like 200 milliamp battery or something, 4,000. It doesn't have a massive battery. It has a pretty small battery. Plus, it's only 3S. How is this flying for so long? So in the past, aerial photography drones or quads or whatever, aerial photography platforms typically ran higher voltage, and in many videos you'll see people explaining that the higher voltage allows for lower current, which is true if you lower your kV as well, but it allows for lower current, and the efficiency gains that you gain are in heat savings and weight savings from smaller gauge wires and various things like that. While that is partly true, how much heat are you actually causing in your wire? And the motors, they're really more wattage regulated than specifically amperage heat. However, they are more efficient at converting voltage and amperage together into power rather than just amperage and less. But it's something about, even back then, something about weight savings in wires. I mean, how much wire weight are you going to save? 10, 15 grams on a 30 kilogram quad? How much is that going to help your efficiency? And the heat. I mean, how much is wire heat going to cause battery loss? I mean, we only fly, compared to how long we're flying these things for, let's say 15 minutes, because that's about how long an aerial photography platform flies for. How much heat can you possibly lose to cause? I mean, we can put LEDs galore on our quads and it doesn't change our flight time, even though the LEDs will technically only run for like 20 minutes if you just plug in a battery. That discussion aside. So heat and weight is a very, very small portion of how efficiency happens. So let's look at specifically the Mavic. The Mavic has a super duper tiny motor. It's got super duper tiny motor. It barely has enough torque to spin this massive 7-inch prop. The code can make it fly smoothly because it has enough torque to manage the prop. That's fine, just for efficiency purposes and the basic function that the thing does. It doesn't have any performance. It doesn't do any performance. If you tried to fly in a Mavic Acro, you'd hate it. It would do nothing. But it's really great at a hover. So how do they gain this kind of crazy, crazy efficiency? So in reality, voltage is not efficient. We only see higher efficiency gains with higher voltage because we are running our performance quads at the limit of what the battery can dish out. And even when we move to 6S, we're still running them at the limit to what the battery can dish out. Where voltage plays a role is when you need more power. And so voltage and amperage. Amperage is like flow, like water flow, and voltage is like potential, how, I guess you could say, energetic the water is. That's a really bad example, but let's go with it. So if your water is high energy or low energy, there is no high energy or low energy water. I guess you could call deuterium high energy, whatever. But high energy or low energy water. So if your water can't flow through this pipe any faster, well, you're going to need to move to higher energy water just to get it to give you the power that you need. So that's exactly how a battery works. If it cannot dish out the power, the amperage, as fast as you need it to dish out, then you need to move to higher voltage so that your amperage falls, and it falls within the battery's ability to dish out the amperage. The gains that we see on 6S are specifically due to that amperage because we are always hammering the battery with amps. Hammer, 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 hammer. We want those amps. Pull, 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 pull. When you go up in higher voltage, you don't need as much amps to produce the same overall power wattage. And so those are the efficiency gains that we personally seen. But in reality, that is the opposite of what is efficient. And that's a much more complicated discussion, which, like I said, I'm not super qualified to discuss, but I'll give you the beginnings of the concepts of, and you can go do your own research, and hopefully somebody else will give me more information, because I sure am not coming up with this information myself. Let's look at ESCs. How do ESCs work? So brushless motors are 3-phase DC motors, and they switch when they have like 11 poles or 14 poles or however many poles, and the power, you should generally know how a basic motor works. There's many videos on it, but basically the poles of the motor, they flip their magnetism back and forth, and they push and pull against the magnets on the bell, and that's what causes the motor to spin. What this means is that the FETs, the big things that usually catch fire on an ESC, need to actually switch on and off. And there's usually one master FET or one timing controller which actually does the flipping, and it flips these FETs on and off. Now, how do you get lower RPM and higher RPM? Well, this is going to be difficult to understand if you don't already kind of have an idea. An ESC works best either off or 100%. The ranges in the middle are not optimal for the ESC, and that's because these FETs need to switch on and off much more often. Because if you know how LEDs work or computer monitors work, the way they work is by flickering. So if you wanted 100% on LED, you just leave it on 100%. If you wanted 50% on LED, then you turn it on and off 50% of the time. So you do that much faster, so it doesn't look like it's off and on. It looks like it's just one fluid stream of light. Well, this is effectively the same way an ESC works and how the FETs work. They are flipping the power on and off really, really quickly. Now, what happens when you give these FETs more voltage? They have to flip on and off a lot more often because you need to lower the amps a lot more. Now, FETs work with amps. They primarily push amps. So when a FET is fully open, it's just dishing out the amps. The voltage is kind of a secondary thing. Amps is the main function the FETs modulate. So if you are increasing your voltage and lowering your amps, your FETs need to switch on and off much more often, and that is not efficient. The switching causes losses. That's pretty shocker. I mean, when I learned that a while ago, but I relearned it, I was like, oh wait, that makes a lot of sense. Now that kind of throws a wrench into the system of how do you design an efficient setup and how do you do, let's say, long range well. Well, our applications are very, very different than aerial photography platforms or various other flying contraptions. We need the performance as well as the efficiency, and getting both of those is really the struggle. So motors are different. I'm not even going to talk about the efficiency gains of motors because it's hard to explain. What I'm just going to say is that the torque, the optimal torque point for the motor is where it's most efficient. If you go too high or too low, it's not going to have the power. It's going to require more power to kind of get the thing to do what you want it to do. So similarly, like a fixie bike, to start the bike going, it takes a lot more energy. Just like a motor, if it's needing to go up from an RPM where it doesn't have the optimal torque, it takes a lot more energy and it's just not quite as efficient. So you want to keep the motor at the optimal torque range, and that is why around 50-ish% based on the motor KV and the construction and everything is where motors are usually more somewhere in the middle. Basically, they're more efficient somewhere in the middle because they're not making their maximum torque at the top unless your KV is too low, and they're not making their maximum torque at the bottom because they're not making their maximum torque at the bottom because these aren't like car motors where they're geared to just give you low end torque and that's it. Totally different area. Don't compare this to cars. Can't be compared to cars. Tesla doesn't work like this. It does sort of, not really. It doesn't work like this at all. So the most efficient setup is going to be an ESC that's either mostly off or mostly on, where the FETs are mostly open or mostly closed, which I'm not 100% sure about the mostly closed, but I'm pretty sure about the mostly open, or just not switching as much, not switching on and off as much. And the motor is at its optimal torque range. And the prop is appropriate for the motor just to be managed, just barely managed. And that's pretty much what the Mavic is. It's using the smallest motor, smallest, lightest motor it can manage for the large 7-inch prop size. I'm pretty sure it's 7 inches, not 100% sure, but I'm pretty sure it's 7 inches for the large 7-inch prop size. And I'm betting that the ESCs inside that thing are not maxed out, but they're closer to the higher functioning point than the lower functioning point on the ESCs, because I think open FETs are more efficient. I'm not sure about that at all, but as long as you have the right cooling on the FETs or it's not generating the heat, I think open FETs are more efficient. Either that or it's the opposite. It's either at the lower end of the function. I would bet the higher end of the function because it's cheaper to have a smaller FET that's operating at a higher end, but it is also more expensive to have it quality so that it doesn't fail on you because you're stressing it. Electronic stress is a totally different topic entirely. Like I said, I'm not qualified to talk about all this. I'm just kind of giving you concepts and ideas to think about because I think it's super interesting. I really wish that people that actually develop this information would write articles that are concise and understandable and, you know, really fun to read. Anyways, that's pretty much the gist of it. So how do we do long range? What is most optimal for freestyle? What is most optimal for racing? Well, that's kind of up to the user and up to the prop and up to everything of what you're doing. But basically, I would say the reason why we would increase voltage is to get out of sag range. And we'd want to just eliminate sag completely. And going from 4S to 5S pretty much does most of that. Going from 5S to 6S does that pretty much completely. Unless you're going crazy racing, you pretty much feel no sag on a 6S battery until it's totally dead. So it's really, really easy to damage your battery if you're not really careful checking the voltage. And it's also why you don't get any low voltage warnings until the very end of your battery when it's already done. And when it's done, it's done. You got to land. So what's going to be optimal for long range? Well, for long range, you can't tolerate sag. If you have sag, you're going to hit that tree because you're diving down that mountain 10 feet off the tree line. So you need to have the voltage. So you have to have a minimum of 5S. You have to do 5S. But is 6S better or more efficient? No, it's definitely not. Higher capacity batteries are going to give you more flight time than higher voltage batteries. That's just how it plays out. That's how the electronics work out. Maybe in the future that'll change, but that's how it is. bigger capacity is going to be better for longer flight time. And a while ago, the flight time record quads, they would use 4S massive 18650 cells, but 4S, not 6S. I think some of them now use 6S, but I still think that a larger capacity 4S might be better for flight time. However, like I said, you need the smallest motor that could spin your large prop, and you may need to give that motor more voltage, and based on what ESC you use, you could technically optimize the electronic situation to give you the best possible flight time performance. But you also have to take into consideration the lifespan and quality of your ESC, quality of your electronics, and if they're actually going to hold up over time. So you're starting to see how complicated these things can get, and this is really just the smallest scratch on the surface. This is just the very beginnings of all this stuff that, like I said, I do not understand. The engineers at DJI and the people that are actually working on this stuff trying to decipher why 4S and 6S feel so different, these are the people that really understand it. They're going to tell you all sorts of math theories and computational numbers and how things work and their testing results. I'm just giving you the information that I've been told. I can't really say anything more than that. I just think it's super duper interesting. But before we go, let's talk about racing. So racing, we went to 6S. We could even go to 8S. We can go to 10S. It doesn't matter. Whatever it is, racers will race, and they're going to go faster and faster and faster, and they're going to push that battery harder and harder and harder. But is 6S better than 4S? Well, I don't know. It's up to you. I would say yes, just because you get no sag, and in a racing situation, you're going all out anyways, no matter what, or even if you're not, you need to have the potential to go all out, so 6S is better. For acro, different story. Maybe 6S isn't as good for acro, because you're not getting the efficiency. And in fact, you may have seen on the previous video, the Xing motor, that quad was flying on a 1300 milliamp 4S, and it flew for like 5.5, and it still had battery left in it, 5.5 minutes with plenty of battery left to go. And it's a 1300 milliamp 4S versus a 1000 milliamp 6S. I was not getting any more flight time. I was actually getting less flight time on a 1000 6S, flying about the same than I did on a 1300 4S. And now it should be obvious that it's probably because I had higher capacity and I had enough power to spin the props no matter what. And the motor was not in its most efficient range, but it was doing better than it did on 6S when the FETs were switching like crazy, causing a whole bunch of losses. But I'm not saying that you should run 5S with 2300 kV or 2600, 2700 kV. No, that's not correct. If the kV is too high and the motors are able to actually spin up that high, they're going to just be pulling so many amps that it's just going to kill everything. But it's the sag that is improved with respect to performance that makes these things fly better. So it's, for acro, it's really nice to have better than 4S. 4S is really kind of the minimum where you can fly, but once the battery reaches that hump point where it's lost its peak performance or just peak energy, then you definitely feel a sag. And when you go to 5S, you don't feel that as much. When you go to 6S, you don't feel that at all. So it's up to you what you want to run. 5S and 6S I would recommend for acro. Going forward, I actually don't know if going up in voltage is going to help it. I don't think it's going to be good at all. In fact, I think 6S might be too much. We may actually move back to 5S in a year because people will realize or figure out why the 5 or just lower voltage seems to feel better. I personally think it's because of the amps. And what I'm doing with my higher kV 6S motors is just giving the amps back to the motor. I don't really care for the super high power. It's just giving the amps back to the motor so that it feels more like a 4S motor because it has higher amps. And that might be an ESC gain, I don't know, but I've tried small ESCs as well. They don't perform very, very well on these things. So I don't know. Lots of testing. I really don't know. I don't know. Don't know. Nobody knows. I hope to know more in the future, but I don't know. Anyways, I hope that was really interesting. And please definitely floss your teeth. And if you stuck with me throughout the whole video, thanks for listening to all of my pretty much ranting. Take care. Bye. Happy New Year. Happy New Year. Bye.